A strong bar magnet is dropped through a coil that's connected to a galvanometer rather. As the magnet approaches and passes through, what does the galvanometer read? So in this case, we don't know which pole of the magnet is falling toward the coil. And for that matter, we don't know which direction the galvanometer is hooked up. So B and D are basically equivalent choices. So it's likely that neither of them is correct. Our other options are deflects to the right, then returns to zero, which is good because it means that we have the current stopping after a while and we don't have a perpetual motion problem. And we have C as well, in which case we also return to zero. So in the dropping of the magnet, there are three different stages. The magnet approaching, the magnet passing through, and the magnet leaving. This is a very important part of the process. So as the magnet is passing through the coil, the magnetic flux through the coil will be constant, which means that it'll have to return to zero. As it's approaching the coil, we can see that there has to be some deflection of the galvanometer because there's a changing magnetic flux. So that means that both C and D have the right idea. But after that, the magnet leaves the coil. And when the magnet is leaving the coil, there will be another change in magnetic flux. During this change, instead of increasing magnetic flux, there's decreasing magnetic flux, which means that the current will be in the opposite direction. And so we can see that C is the most likely answer, and that is in fact correct. As the magnet's approaching, it produces a current that deflects the galvanometer in one direction. As it's passing through, there's no change in flux. And as it's leaving, it'll produce a current in the other direction. It means that even if we don't know which pole of the magnet is moving toward the coil, we can still make a good judgment of exactly how that coil will behave. Question 8. What is the main difference between a motor and a generator? You'll notice in any of the pictures of motors and generators that they have fairly similar properties and fairly similar structures. So we have a few options here. Let's quickly go through them. The magnetic field in a generator points in the opposite direction to the one in a motor. That doesn't sound very likely because we can orient a motor in any direction we want. So it's probably not A. Current flows in different directions for each device. Once again, we can orientate the motor however we want. So it's probably not B. And in, for example, an alternating current motor or generator, then current will be flowing in both directions anyway. Motors and generators are rotated about different axes. We know that in both cases, we're rotating it so that the coil is perpendicular to the magnetic field. So that's not the case. And our last option is the coils of a motor are turned by electromagnetic force, but the coils of a generator are not. And this is in fact the correct answer. If we turn a motor around by hand, we'll produce an electromotive force that will in fact create a voltage across the motor, even if it's not connected to a battery. And if this happens, we've generated a voltage, so we've got a generator. Question 9. Which choice correctly shows the direction of the eddy current induced in a metal disc as it falls downwards through a magnetic field? So this yellow disc is on its way down toward the ground. Now as it passes through the magnetic field, it will try and resist the change in flux across it. That's Lenz's law. So if we look at all the situations, we have two linear currents and two circular currents. Now we know that linear currents do not produce a magnetic field, or not a linear magnetic field that would resist this one. Instead they produce a circular magnetic field which really wouldn't mesh very well with either of A and B. So our only options are C and D. So in C and D we have a circular current which will produce a magnetic field. What we want is that magnetic field to oppose the magnetic field created by these magnets. So if we look at which way the current is flowing, it'll be moving in a clockwise direction. So the North Pole will be pointing that way and the South Pole will be pointing that way. In D, that will actually be in the same direction as the existing magnetic field. So the induced one will be supporting the existing field, and we can see that D won't be the right answer. In C, that induced magnetic field will oppose the field produced by these magnets. So C is the correct answer.